Okay, so we've already been focusing on finding mins and maxes, and now we're going to apply that idea with our favorite type of problems, word problems. All right, so here's a classic example. Find two numbers whose sum is 60 and whose product of one times the square of the other is a maximum. All right, so there's usually two things with these optimization problems. Okay, we have our primary equation. What are we trying to maximize? All right, what are we optimizing? Might be minimize. All right, so our primary equation, we want the maximum product of, so I'm going to just write P for product, one number times the square of the other. And always with these problems, there's some kind of constraint. Okay, what's the limitation? And in our case, their sum has to be 60. All right, so you focus on, you have your what are you optimizing function. You know the constraint. So now you want to try to get the primary equation into one variable. In order to do that, you just need to solve the constraint for one or the other. Okay, so we have 60 minus y. Plug it in now. So we have 60 minus y times y squared. Okay, multiply it out. Oh, come on. All right, there we go. All right, and now to optimize it, we just have to take the derivative. Okay, so 120y minus 3y squared. Solve that for 0, so we're trying to optimize it here. We can factor out, let's see, 3y, yep, okay. So we get 40 minus y. So we have two possible critical values, 0 or 40. In this case, 0, if we had that as our number, that's not going to give us a product more than 0. So we can ignore that. Let's see, if I plug in, let's analyze 40 in our derivative function. Okay, so on the right-hand side of that, it's going to be negative. On the left-hand side of that, it's going to be positive. So we are talking about some kind of relative maximum here. All right. And then we need to go ahead and find x. So we have 60 minus 40. X is 20. So find the two numbers. The numbers are 20 and 40. All right. As we move forward, we're going to see a lot of the other classic types of problems here. This one, you're limited on some kind of rectangle perimeter, and we need to maximize or minimize an area. Okay, so a good way to do this kind of problem is to draw a picture. All right, so we have this picture. We could call one side x, one side y. Come on. All right, so we have x and we have y. So we are our primary equation. We're looking for the maximum area. So the area of this would be x. Whoa. Let's undo that. All right, primary. There we go. Area equals x times y. Our constraint in this case, it's 8 inches long. So the perimeter is 8 inches. Okay. 2 times x plus y. So we have our primary, we have our constraint. Let's solve for one variable. All right, plug it in. Simplify. Take the derivative because we want to maximize it. Check for critical values. Okay, and it looks like y it would be 2. Okay, so if y is 2, let's just verify that that is actually a maximum. This one's actually easier. Instead of doing a sign chart, the derivative of this function, okay, the second derivative of the area, is just going to be negative 2. And that's less than 0 for all x, or for all y values, let's say that. So it's concave down all over. So that means we're going to have a maximum there. All right, and so now let's find our x value. 4 minus 2, x equals 2. So what dimensions of the rectangle will produce the rectangle with the maximum area? It's going to have to be a 2 by 2 inch rectangle. All right, everybody loves ladybugs, right? Let me change my color here so we can have some ladybug fun. A ladybug farmer. We see them all the time, right? Has 500 inches of fencing and wants to fence off a rectangular field that's on a river. All right, so we have, I might as well draw my river. And he wants to build a fence. So we're only talking about 3 sides here. All right, so what are the dimensions that have the largest grazing area? So when we talk about our primary equation, we're trying to maximize area here. Our constraint equation, we're limited on the amount of fencing we have. Okay, and then we can solve, this one would probably be easier to solve for y. So we get 500 minus 2x. All right, and let's plug that in. So we have 500 minus 2x times x equals 500x minus 2x squared. Okay, we could take the derivative of that pretty easily. All right, optimize that. So we get 500 equals 4x. Okay, so 125 equals x. And again, since this is linear, I'm going to just look at the second derivative here, which is going to be negative. So a is concave down, which means that x equals 125 is a relative max. Okay, so let's find y. Y equals 500 minus 250. So y is 250. So the dimensions that we want are going to be 125 inches by 250 inches, and the 250 is along the river. All right, same kind of problem for the next one, but now we're changing the wording. All right, this time we want an exact area, and we're looking for the least amount of fencing. All right, so when we talk about our primary equation, now we're talking perimeter. Okay, so primary, we're talking perimeter. Our constraint this time is our area. X times y equals 10,000. What does 10,000 square inches look like? How big is that? Do you think that's as big as the classroom? It's a good question for a whisk. All right, so I solved this for y. I'm going to plug it in. There you go. All right, this isn't too bad to take the derivative up to minus 10,000 over x squared. All right, so to make this easier, I'm going to combine it into one equation. Come on. All right, 2x squared. Not working out too well, is it? Minus 10,000 all over x squared. Okay, go and solve that for 0. I don't have to worry about where it's undefined because we're not going to have 0 as one of the lengths. That wouldn't give us any area at all. All right, so if I factor out a 2, we'd get x squared minus 5,000 equals 0. So we're looking for where x squared is 5,000. All right, and so that would be the square root of 5,000. I can disregard that negative square root because we're not going to have a negative length. And if you care, it's about 70.711 inches. All right, so if we're looking at finding what's the least amount of fencing required, okay, plug in your x. Your y is 10,000 divided by the square root of 5,000. So the least amount of fencing required, if you get decimals, is approximately 282.843 thousandths of an inch long. Okay, so there's one more problem that I'm going to go through today, and it won't take too long. All right, it's completely different. Now we're just talking about a graph. All right, so find a point on the curve. So let's put that on there. Y equals x squared. Closest to the point 30. So maybe it's about here. So hopefully you remember different things on how to find the distance between 2 points. All right, so we're trying to minimize this distance here. All right, so we know that distance between 2 points, you can use the Pythagorean theorem or the distance formula. X minus 3 quantity squared plus y minus 0 quantity squared. All right, I'll simplify that a little bit later. And remember, this is our primary. Our constraint, however, is y equals x squared. So instead of writing y, I'm just going to write x squared. I'm going to go ahead and multiply this out. And remember, I'm going to write x squared instead of y. Now, one thing I want to note here is we can optimize. Let me highlight it right here. We can optimize. If we minimize this function, then we'll minimize the square root. Okay, so this is just going to save us from doing a lot more work. So I'm going to call the inside, what is that, the radicand or something? I'm going to call that r of x. That's an x, okay. 2x squared plus 6x plus 9. So let's go ahead and take the derivative. And that was a tough derivative. All right, we're going to find where that's 0. All right. Oh, I changed that sign magically. Don't want to mess that up. Okay, so we get 3/2 for our x value. And again, it's linear. This is a linear equation, so r double prime is always greater than 0. So that means r is concave up, which gives us a minimum value whenever we have a critical value. All right, so plug this in. Y equals 3/2 squared. So that's 9/4. So find the point on the curve closest to that. That would be 3/2 9/4. That would be the closest point on that function to 30. All right, so that's all we're going to do for today. If you want to work on your worksheet, probably a great idea. If not, I'll see you in class.